And last but not least, in Chapter 6, we're going to take a look at enzyme regulations. Let's get going with that. In cells, enzyme rates must be continuously tuned or adjusted to keep them kind of responding to the needs of the cell. Regulation that depends on the interactions of substrates and products with an enzyme is generally called substrate level regulation. An increase in the substrate level generally results in an increase in reaction rates like we saw last time. But when you see an increase in the product level, that is what's being made by the set of reactions, you tend to see a reduction or a lowering of the reaction rates. And so there are 2 or 3 general mechanisms we can look at, and we can probably break them into 2 main categories. First of all, allosteric regulation, and then secondly, covalent modification. And those covalent modifications can be reversible, or they can be permanent and unreversible. Now, most of the time, when we have a biochemical pathway like this one over here on the left, where A is converted to B, and B to C, and C to D, and D to the final product by 4 enzymes E1 through E4, often we will see the product acting on an enzyme at the beginning of the pathway. So P here would act on enzyme 1, and in this case we'll often see the product negatively feeding back on the activity of enzyme 1 to turn off enzyme 1. So that's called negative feedback. Now there are some cases of positive feedback, but we'll look at negative feedback here. So that's feedback inhibition of the first enzyme in the pathway by the product of the pathway. So probably the most common mechanism for feedback inhibition is allosteric regulation. So let's just take a look at this pathway on the right here. And what we're looking at here is the pathway that converts the amino acid threonine at the top here to isoleucine, another amino acid, at the end of the pathway. And so there are 5 enzymes here which are involved in converting the threonine to isoleucine. And the first enzyme is called threonine deaminase, and there's enzyme 2, 3, 4, and 5. So if this pathway is working optimally, and we've got all the isoleucine that we need in the cell, there's no point in the cell converting the threonine to isoleucine, continuously. We need to shut that process off if we've got all the isoleucine we need for translation. So if isoleucine were to impact, let's say, enzyme 4, so if isoleucine turned off enzyme 4, so if enzyme 4 was product inhibited, then we'd still have enzyme 3, 2, and 1 working, and that could be potentially wasteful if these are using, for example, ATP or GTP or that kind of thing. So if isoleucine as a product inhibits enzyme 1, then 2, 3, 4, and 5 won't have substrate, and so they won't be doing their jobs either, and that's more efficient for the cell. So isoleucine can bind to an allosteric site on enzyme 1, so on threonine deaminase, and turn off enzyme 1 so that we shut off this pathway. So that's an example of product inhibition. And now we can think about allosteric regulation as kind of either being inhibition, like we just saw, or activation. So allosteric enzymes in general have 2 conformations. That means just 2 shapes. These enzymes have one conformation where they have an affinity for the substrate, that means they readily bind it, and one conformation where they don't bind the substrate. And so allosteric regulation takes advantage of these 2 states by either converting the enzyme to a state where the enzyme doesn't bind the substrate, it lowers affinity, or it stimulates the affinity of the enzyme for the substrate. So the 2 mechanisms that we can look at here, on the left is inhibition. So this is allosteric regulation in an inhibitory manner, and then this is allosteric regulation in an activational manner. So The enzyme we'll look at here that's going to be inhibited, it's got its catalytic subunit C and a regulatory subunit R, and catalytic site is obviously, or the catalytic subunit has got an active site where the substrate can bind, and when that happens the substrate is converted to the products, and so at the top here the enzyme is working perfectly fine. An allosteric inhibitor binds to the regulatory subunit in an allosteric site, and that turns the enzyme off, and so the binding of the allosteric inhibitor is reducing the affinity of the catalytic subunit for its substrate, and subsequently we don't have product formation. Now the kind of flip side of that is that we could have an enzyme which is normally, when it's not bound to an activating allosteric regulator, it doesn't do anything. It's got a low affinity for the substrate. Now if you bind the activator, that means that the catalytic subunit of the enzyme has a high affinity for the substrate, and the substrate is converted to product. So that's activation via allosteric regulation. Many of these allosterically regulated enzymes demonstrate what's called cooperativity, and so is what you see is that if you have multiple subunit enzymes, when you have multiple allosteric regulators binding, you see significant drops in activity with every subsequent binding of a negative regulator, or you see significant activation with the binding of an allosteric activator. So that's called cooperativity. And so negative cooperativity is when you see significant decreases with every single allosteric regulator binding, and positive cooperativity is when you see significant activation of enzyme activity with subsequent activator bindings. We can also have the covalent modification of enzymes, and that can be the regulation of activity by the addition of certain functional groups such as phosphate groups, methyl groups, and for example acetyl groups. So probably the most common mechanism here is the reversible addition of a phosphate group, and that's called phosphorylation. And so that happens when you have the transfer of a phosphate from an adenosine triphosphate molecule to either a hydroxyl in a serine, or a threonine, or a tyrosine in a target protein. In bacteria this also happens too, and there the target residue is often a histidine amino acid. And so this can either turn on an enzyme, or it can also turn off an enzyme. And the reverse of that phosphorylation is called dephosphorylation. So phosphorylation is done by kinases, and dephosphorylation is done by phosphatases. So let's take a look at an example here. And the example is how adrenaline works on cells to stimulate the breakdown of glycogen, so that you have the ability to release glucose and to increase the rates of oxidative phosphorylation, which leads to a upregulation of ATP, and therefore the ability to fight or run away. So here's a glycogen chain at the top here, and here's an enzyme, glycogen phosphorylase A, and this enzyme can exist in a phosphorylated form when it's active, or a dephosphorylated form when it's inactive. Now when glycogen phosphorylase is phosphorylated by a particular kinase called phosphorylase kinase, is what glycogen phosphorylase A does is it breaks down glycogen to give us glucose 1-phosphate, which can be fed into glycolysis to drive cellular respiration. And so we can convert the inactive form of glycogen phosphorylase, the B form of the enzyme, to the active form of glycogen phosphorylase, the A form, by using phosphorylase kinase. So phosphorylase kinase is stimulated, it's turned on itself by the binding of adrenaline to certain cell surface receptors. And if we want to reverse this process, if the adrenaline response has stopped, then we can have phosphorylase phosphatase, which reverses the activation of phosphorylase A back to phosphorylase B. Now it seems that it's dinner time and everyone wants their dinner, so everyone's very, very eager and friendly this evening. So let's finish up this so that I can feed the boys and talk about covalent modification in the form of proteolytic cleavage. Now this is a one-time irreversible removal of part of a polypeptide chain. So you often see this proteolytic cleavage working on enzymes produced by the pancreas, so things like trypsin, chymotrypsin, and carboxypeptidase. So the pancreas releases this whole suite of enzymes into the small intestine. So we've got trypsinogen, chymotrypsinogen, and pro-carboxypeptidase here, and the epithelial cells produce what's called membrane-bound enterokinase, and that can stimulate the conversion of trypsinogen to trypsin, and then the trypsin acts on chymotrypsinogen to produce chymotrypsin, and then the chymotrypsin cleaves pro-carboxypeptidase to produce carboxypeptidase, and then these three enzymes in green are involved in the breakdown of proteins in the small intestine, and so these are all activated by the cleavage of these precursor proteins here. So that just about wraps it up. It's clearly dinner time for the boys. That's the end of chapter 6, and so we'll be coming back next time with some new topics, and I'll see you soon.